Good afternoon. Thank you for being with us today. I'm happy to see all of you here online and on site. Delighted to welcome Professor Stefana Parascho today. She's the Tenure Track Assistant Professor and Director of the Laboratory for Creative Computation here at EPFL. Today she's going to give us a talk titled The Robot in the Loop, Multi-Age Construction Approaches. You know now the formats. We have 1 hour in total. Stefana agreed to speak for 40 to 45 minutes, and then we have time for questions at the end. And if you have urgent questions, you can ask them right away. If not, we'll take them up at the end. But after the presentation, I would like to thank Stefana for her availability, of course, the entire CS team once again for organizing this event. Now, Stefana, the floor is yours.
Thank you. We are recording it, right? Just to be sure. All right, so thank you very much for the introduction and for the invitation. I am very happy to give this talk as part of BCIS. This is my first year here at EPFL and possibly my first lecture here, I'm not sure. No, my second, I gave one people. Anyways, I will start with a quick background about myself. So I started studying architecture in my home country in Romania. And after 2 years, I left it to finish my studies at the University of Stuttgart, where I did my diploma and finished my master's studies. And that's where I had my first contact with robotic construction in the context of architecture. Still, after my studies, I moved to Zurich, where I did my PhD at ETH with grammatical research, and I really focused my work on multi-robotic assembly techniques. And then in February 2019, I made a bigger jump to Princeton University, where I was assistant professor for 3 years. I continued my work on robotic construction methods, specifically multi-robotic methods, and expanding towards new applications and looking at the long-term implications of digital technologies for design. And now, since March 2022, so a bit over half a year, I started here at EPFL, where I'm planning to continue the research. It's still a question mark. Soon it should be more specific what exactly we will be doing here. But specifically, we're planning to focus on human-robot collaboration for construction. So I run here the Lab for Creative Computation, Circle. In short, it is a more or less seamless continuation of the lab that I led at Princeton as well, which is called Create Lab. So not to be confused with the Create Lab here at EPFL, but we changed to Circle. And you can find us at circle.org. So what are we actually doing here? We really focus on combining design with engineering and with robotics and with construction. So we have expertise at the lab from architects to engineers and artists. And I'm particularly interested in this relationship between robotics and the engineering side and the design perspective in architecture. So rather than just thinking about new material processes and how we implement them, I really like to explore where these change the way that we design and how we perceive our architecture and design. So why robots? We look at robots, and particularly industrial robots, as generic machines that have specific qualities such as precision, but we look at them from a different perspective than the way we're used to seeing them in the manufacturing industries, where they are typically used to automate very repeatable tasks. So the same object is being produced hundreds of thousands of times. The robot makes the same movements hundreds of thousands of times, such that implementation effort and costs are minimal. We've seen similar intentions in construction even since the 60s. This was kind of a robot from the 60s, which was still a manual machine that had to be pushed around, but it automated the bricklaying and mortar laying process. But typically what we see in the construction industry is that we automate standardized processes that don't allow for customization or adaptation, but they're based on the same processes that we know from centuries of analog construction. So instead, in my field, we look at the potential of digital technologies such as robotic fabrication, precisely in dealing with non-repeatable things. So individual constraints, bespoke elements, and differentiation. Basically, a robot doesn't care whether it makes the same movement 1,000 times or it makes 1,000 different movements. So there's clearly potential in robotics for bespoke tasks if we focus less on automating and replacing humans and more on what can each of these two parts do better than the other and how can we combine these two. So we've seen lots of developments in academia in this direction. The field is now about 15 years old. From creating differentiated walls to spatial structures that require individual placement of elements. So all of these were built with robots and new material processes. But at the same time, the industry is really still concerned purely with the automation of standardized processes and the increase in productivity of that way. So what all the academic projects have in common is they've really looked at questions of how can we build new complex geometries, how can we optimize construction. But I think what we're not asking enough is what do these technologies enable us to do as designers and as engineers that goes beyond complex geometry. So how can we access maybe new applications and new unexpected goals? So in my own work, I like to take a few steps back and I like to think about the role of the machine and our own relationship with technology from a designer's perspective as well, and look at where does the human belong in this loop rather than where we can remove them from it. And in particular, my work revolves around using multiple machines and humans, but this focus on multiple agents is really in order to move away from the single task processes, which are more applicable to automation, but to explore how can multiple agents collaborate with each other, take on different tasks, and what sort of possibilities evolve from it. So I'd like to walk you through a few projects to give you an idea of the questions and applications that I've been dealing with and that I'm slowly setting up here. Starting with the relationship between structure and fabrication. This is about a project searching for ways of transparent and reciprocal information flow between design, structure, and robotics. So the Brick Labyrinth, it was a teaching project that was developed together with students of the MAS in digital fabrication at ETH Zurich during 11 weeks. And the challenge here was really to combine planning and simulation with the physical implementation and the material tests necessary for such a material system as brickworks. So brick construction is really a long-established tradition in robotic assembly. If you're a bit familiar with the field of construction robotics, it's been one of the first processes to automate, and there's been projects and projects and projects tackling brick construction. But what the reason we chose it and what we did with this process was to try to develop a process that is completely using only dry stack bricks, so no glue or mortar, to make the reversible process and also to scale it up. This was one of the first projects that we did in the fabrication hall at ETH, and it also served as a test of how far can we scale things up. So the focus of the project was really on developing means of simulation and visualization that allowed for the safe construction of the 10,000 brick structures, while at the same time trying to push the limits of the structural system that we chose. So students used physical tests in parallel with developing their own simple geometric simulation to come up with quick ways of evaluating what is buildable and what not. If we have the robotic precision, but this material system that works with heavy bricks, which clearly has some dangers with it. So the goal was really to increase the height and this angle of these leaning walls through the precise placement of the bricks. And in this case, the walls are only stable due to a double layer system that the students found through this physical explorations. And stability was, of course, one challenge, but the robotic construction remained the other. So the complexity in the design had increased with the fabrication, since we had to develop a sequential assembly process where the walls had to be constructed in an order that ensured stability, reachability, and no collisions at the same time. And since we're talking about multi-agent construction processes, in this specific project, we were aimed at full automation. We were not really looking at the role of the human, particularly because of the dangerous nature of the construction. So there was a purpose in keeping humans away from it. Instead, we used different types of robots of different scales and sizes to take on different tasks. So you've seen the small robots that are prefabricating these brick stacks, which are then picked up by the larger robot and placed in position. And in the end, this allowed us to build the lab in less than 3 weeks, and it consisted of about 10,000 bricks. Less than 3 weeks doesn't sound so fast. It is fast for us because we run all these processes in manual mode and testing mode because we cannot test them for robustness as you would in a factory. So every single move is an experiment in itself. If you see them in real time, they move really slowly. So it was an achievement for us. Yeah, I think the takeaway from this project was that, for any construction process, we can't really focus individually on a highly specific problem like the sequencing or the placement of the bricks, but we need to consider all the design factors or all the constraints that come together. And that can only be achieved through this combination of physical testing and computational simulation prediction. So this brings me to my next project, which specifically dealt with these complex constraints, such as they result from multi-robotic processes in which the robots work together. So this is my PhD thesis, which focused on cooperative robotic assembly techniques for the construction of bespoke space frame-like structures. And by using the robots cooperatively, so compared to the previous projects, they don't work separately on their own thing, but they really work together. And it allowed me to build spatial structures that don't need any additional form or false work anymore, because one robot can always serve as a support. So in a simplified way, the construction method really works as follows. One robot brings an element, a second robot brings an element, the connection is made, in this case, by humans, and then the other robot can continue. So there's this alternating process, such that one robot is always connected to the structure, and that gives it stability, that gets rid of the need of any sort of guide structures or supports. But really the trickiest part, or the biggest challenge, was less developing this robotic procedure, but dealing with the highly complex dependencies that emerge from the design parameters that can't really be addressed intuitively. So I'll give you a quick example. When I started looking at this system of space frames, I searched for a new type of connection that would allow for a simple fabrication and for the geometric freedom that I was looking for. So I didn't want to use any prefabricated additional elements, which require extra logistical effort and fabrication effort. And instead, I proposed an open node where only 2 bars connect to one another in a point. However, of course, what happens when we shift these bars in a node is that it leads to bending moments in the structure and it reduces the stiffness. So in order to counteract this effect, I introduced a second connection point in each joint that result in these close triangular connections that dramatically increase the stiffness. And while this solved the structural problem, it led to very, very specific geometric constraints. So at every step of the construction, every new rod, it had to connect to the existing ones in at least 2 points. So it had to be tangent to the 2 existing bars in 2 points, which means that its position in space was predetermined, or it could not be chosen arbitrarily, but was a result of the parameters. And it leads to a solution space of where could this bar lie that is more complex than it seems. Particularly, there's these areas where there is no solution, which have to be taken into account when we try to design the structure. And while it's kind of understandable in the graphics, when you have a node with tens of connections in there, it's really difficult to intuitively understand where the bars should sit and should lie. So it's really hard to design with these types of constraints. And this little shift in the bars, it It really defined both the local and the global configuration of the structure. And with the global configuration, it also defined its structural behavior. So these are just three examples with identical node locations, but with different connections between the nodes that shows how unpredictable the structural behavior was. So what I'm saying is that this tiny little shift for designing a structure and for a designer, it turned into quite a bit of a nightmare because it's really hard to control these parameters. So we need to think about, besides developing the computational tools of to be able to work with these parameters, also ways of analyzing and visualizing these things so that designers can really work with it. And of course, besides the geometric complexities that had to be solved, the actual physical materialization process also goes into the design process. In this case, I worked with material connection that was both easy to execute and very strong, welding of steel bars. The welding process is implemented manually by humans, while the robots are used purely for positioning and holding of the parts. And the reason for this is really because I was interested in identifying the processes for which the robots are better than humans, which is holding elements in space precisely and for a long time. And then vice versa. So dealing with very complex movements and little tolerances is something that humans can do very, very well. And that's partly what led into current research that I'm doing, which is on identifying these ways that humans and robots can work together beyond necessarily the separation of tasks. Now, besides the material processing itself, we still have the challenges of the robotic construction method. So of course, working with two robots in the same workspace where they can reach within the same space and within a constantly changing environment, because the structure is constantly adding, it's kind of predestined for little catastrophes, meaning collisions. And again, being active in a discipline that relies a lot on intuition and on human creativity, it's not very easy to address these highly unintuitive robotic challenges. So we use path planning here. We connected it to existing path planning algorithms, and we're able to introduce this into designer software so that we can work with it. But really the challenge is to bring together these different types of solution spaces where as a designer, you work in a two-dimensional, three-dimensional Euclidean space, and then the robot has its own six-dimensional rotational space, and it just becomes very tricky to handle intuitively. And yeah, all of this led to a sequential process in which the structure is basically designed and generated in the exact same order that it is fabricated, for that exact reason that one can then check and find solutions for the reachability and for path planning and for the robotic constraints at every point of the design process, rather than designing a structure and then trying to have it fabricated and realizing it's just not doable because of the constraints and limitations of the robots. So this is just an example of one of the demonstrators that we built that consisted of over 300 elements. And then we did some very professional load testing. It behaved as expected. Yeah, what I want to say with this project is that using the digital technologies that we have available, so as designers, it can very quickly turn into a rabbit hole of dependencies and all sorts of unintuitive problems that designers are not typically prepared for. So this makes the acceptance and the application of such technologies a lot more challenging than in non-design-based fields. Building up on the previous two projects, the following one, it combines basically the brickwork and the multi-robotic assembly techniques. The light bulb, it's a collaboration with SOM Engineering and with the Form Finding Lab at Princeton University. And it resulted in a prototype that we exhibited in London in 2022. Unfortunately, only for a few days before the COVID lockdown, but we still got it built. So that was a success for us. We focused on finding ways of constructing vaulting structures out of heavy brick material again. based on the methods that I had developed for the steel structures. So using the two robots to collaboratively assemble an arch such that it does not require any sort of support structure or additional structure, guide or support. And the challenge, again, it was, well, there were many challenges, but maybe the main one was in designing the structure in a large interdisciplinary team with different sort of vocabularies and expectations. What it resulted in was a glass brick vault that was built with two robots by starting with this cooperative arch that could be built by two robots working together, and which served as a backbone also structurally, and then continuing with the robots working individually from the arch outwards to complete the structure. And instead of working through individual design options, sending those around through the team, we specifically used the robotic setup to identify and visualize the design space that spans between them, and to find out the influence that the sequence and the building direction had on possible design. So, for example, the vault is shaped upwards towards the ends, not only for structural reasons, it did help structurally as well, but also because of the reach of the robots. Where they have to work together, they need to reach a bit lower, and then they start building about their own heads, so to say. So it was a result of both the reach of the machines and the structural requirements. And all of these temporal dependencies, so where do we start building and where do we end, they're also become quite visible in the pattern and the sequence definition that we came up with, which had to ensure stability not only at the end, but also during construction at every step. So, for example, we calculated a sequence such that every brick, when it's being placed, it has two sides that are where neighboring bricks exist, where you can connect to, so it never just sits on one side, so that it doesn't just fall off for no reason. We did use glue in the structure for several reasons. One being that this was exhibited it was built during the exhibition in a publicly available space, and we had people running around, so we really didn't want to risk anything. But also to ensure the stability during construction. So we had form finding done for the final shape to make sure it's only under compression, not for every step of it. We did have an analysis to check every single step to be sure that it was stable, but the design process was not made such that at every single step it would be stable without the. And I have a short video that I would like to let run, and just looking at the sound. I don't know if it goes through Zoom. Otherwise, I hope it's not super boring for the ones watching, but I was just gonna let this run. Just in case the sound isn't working, I'm just gonna randomly speak a little bit so it's not so awkward in the recording. We tested everything in the lab back at Princeton, and we did quite some prototypes over there with concrete instead of glass, because cheaper and easier to make. And then we moved everything to London. We had two robots that we borrowed from a robotics provider over there that we set up locally, and then built it all in situ. You can see the central part. So we first built the arch and then kind of the first 4 rows to really make it, ensure that it's stable. Also using the robots close to each other, so they were always placing a brick pretty close by, so that you get the support on the other side. And then they started building outwards in the winter. And we had some half bricks to make up for the geometry, the natural gaps that would come up from the anticlastic geometry. They sit somewhere in there. Right. Sorry if it didn't have sound. It's a bit sad to watch 3 minutes without sound. But you can find it online if you really want to see it with the sound. So yeah, this brings me to my current project, things that are going on right now at the lab, where I'm looking at applications that go beyond the construction of complex geometries. So zero waste is one project that I started at Princeton University in collaboration with Aaron Bessler, a design professor there too, in which we investigated what role robots could take on in monitoring existing structures and engendering material reuse. So I'm currently continuing this line of research here at EPFL in collaboration with cooperatively. Back at Princeton, we started by looking at the life cycle of materials and how much waste is produced in construction, and identified 2 main questions. So how can we work with the existing material that's currently in use in buildings, and how can we plan and build new buildings, or even those built out of reused materials such that they specifically facilitate the reuse of the material in the future. So we went all in. We handpicked a number of timber elements from the local recycling facility, which we then assembled into a shed, this time by hand. This was not built by robots, built by students. That was meant to be representative for the typical American wood frame construction. So it's really the sort of material system that is widely used in the US, and what we wanted to work with there. And then we looked at 2 topics. So on the one hand side, how can we use robots for the disassembly and for the reconfiguration of such structure, going back to these advantages that we identified, that robots can serve as support elements and they can take on different tasks and not just assemble things. And the second question was how we can develop a scanning and tracking system that does not only recognize material components and stores their information of their use, but that also helps visualizing this type of information for non-expert users to increase the awareness for reusability and material history. So these are results of the first implementation of this case study that we split up in 4 phases, and in each phases we explored different spatial process. So the first one was pure disassembly by using 3 robots this time. The second phase was on disassembly and then using the same material to reassemble parts of the structure. And phases 3 and 4, they're trying to get the reconfiguration done in the same process as the disassembly. And we're now expanding this approach to having a more automated planning for real-time reconfiguration of structures. It's a project that will start early next year, so hopefully pushing this forward. And at the same time, we're also looking into the reuse of other materials, not just wood, and particularly for Switzerland. I have a PhD student that is co-directed by Corentin Fivet as well, who is looking at inert waste, so materials that cannot be burned. So specifically at concrete and bricks as they come out of building construction waste. So he's looking at the workflow of concrete and bricks, these types of materials as they come from demolition sites, and where we can intervene to make use of these materials, and think about where we can use machines such as robots to reuse and re-employ these materials before they're being basically turned into filling for new concrete. in the best case scenario. So by making use of robotic precision in orientation and placement, we can work with these materials of unknown shape or unplanned shape. But in this case, really the robot is also a placeholder for larger construction machines, such as gantries, since construction operates, gantries, such as cranes, I meant. Since construction operates at a very different scale. So we're looking at the capacities of robots, but also thinking about what do existing large-scale construction machines, what sort of capacities do they have, and how can we augment them, improve them to make them usable for this type of scenario. And yeah, I actually, I'm faster than I thought I would be, but I want to wrap this up with a project that's very different, that actually doesn't use robots at all, but focuses on media technology and how it can shape public space. Social Signals is, it's a project that looked at how we can use new technologies to improve our spatial experience. And it started and focused particularly on the pandemic scenario. This is also a project that started at Princeton that we are continuing right now. So it started really 2020, where we were quite intrigued by how inflexible and inefficient the static markings were with regards to social distancing. So we wanted to see a more dynamic system that can utilize human movement to adjust the type of visualization that we see on these types of markings. So what we did is we proposed a smart projector system that consists of a projector, a mini computer, and a camera, and it can capture people's locations and then compute safe movement trajectories or trajectories to begin with. And ultimately, it would project these trajectories on the floor as a type of indications to guide pedestrians in public spaces. We use a deep learning-based approach for the pedestrian detection. So we were aiming at having a system that allows to deploy the projector in as many different types of spaces as possible, while still somewhat accurately detecting people. And then we developed a visualization that was based on shaders, mainly to allow for even more adaptation than we anticipated. So as the pandemic evolved and social distancing did not really work, slowly disappeared from our lives, we were surprised to still find out that our system could be very useful in the context of public space, as public space gained a very new perception and role. I think people were really eager to spend time in public spaces, and we moved away from focusing on how to distance people, but rather to a visualization that could help them bring people together and connect and interact. And yeah, we did that by playing with the hardness of the borders of these blocks that we visualized as they're facing one another. And I have some impressions. We set up the installation at the state that it was. This was end of 2021. We set it up at Princeton in the architecture school on a landing of a staircase, which had relatively high traffic. And we looked at how people interacted. We were happy to see that people really engaged with it and played with it. And basically, it turned them into spending a bit more time at a certain spot. And right now, we are looking in expanding the system and looking at new types of visualizations, what sort of behavior this can trigger from people using them. And we want to expand it into a bigger system with multiple projectors, and we're looking at setting it up on campus here, somewhere on the bus of it, on the other side here. So somewhere on a covered area that is still relatively dark, that's what we're looking for. But hopefully we will have it set up early next year to play with it a bit more. So yeah, this is where we are right now with the research. We're focusing on a lot of questions around humans in the process of robotic construction, especially how we can go beyond optimization processes and beyond solving problems in order to just materialize certain types of geometries, but to explore creativity and the impact that robotic technologies and machines in general can have in the creative process. So we're looking at questions like how can humans and robots co-design structures, and if there's any added benefit to it, what parameters there, what constraints could be. This is a project from Ayla, who is a PhD student I'm advising at Princeton still, and she's really exploring how humans and robots can work together, not just for dividing tasks, but as somehow equal partners in a creative process. So in this case, the robot places a block and then she tries to fill the space within it, and the robot places a new block, etc. And what she was interested in is really the impact that this has on the creativity of the process. So if you ask a human to just fill this frame, they would probably use rectangular blocks on top of each other to find a solution that's relatively good. But by using the robot to set types of constraints, you get a lot more exciting and creative outputs. And she's also been looking at this type of co-creative process at larger scales. So our goal is really to find possibilities for humans and machines to work together throughout the entire architectural process. So not just for the execution phase of a certain material process, but find out where we can engage from the earliest design points with the machines and what this could lead to. And yeah, we're also, something I wanted to share is some work we're doing on getting this type of processes, materials, and knowledge accessible to students and to the design community in particular. This is a collaboration with a colleague from TU Munich, where we're trying to set up a sort of platform which is particularly targeted at design students to transmit this technical knowledge so that they can jump in quickly into working with these machines, and we can see more engagement there. And yeah, this is actually where I'll end. I've never finished. Now I have. Thank you very much.
Thank you. Thank you very much. Please let me say some words closing for this seminar. Thank you, Stefana, for your presentation today. Thanks to all of you online and on site. Regarding our next events on next Monday, we're looking forward to work on Chris Wiggins from Columbia University. And then on the 19th of December, that's 2 weeks' time, we are looking forward to see Gabriele Manoli explain us what he's up to in his lab. This is going to be our last Get to Know Your Neighbor talk for this year. Thank you. Goodbye.